Hello, my name is Emmanuel Bakare, and today I'll be taking you through exploring the math of thresholds. Thresholds are bounds, upper and lower bounds, and I'll be showing methods using numerical methods, which is in mathematics, iterative methods for predicting where something should be. So, who am I? My name is Emmanuel Bakare. People call me Bachman. I'm a senior development engineer at Twilio. I also, on the side, build solutions at Baseline HQ Cloud. One of them is called Craft, where we use some of these methods for things like right sizing, request and limits in Kubernetes, automatic right sizings. So you can check out the product there, cost-crafted Baseline HQ Cloud if you like it. What is a threshold? A threshold is a boundary at a certain time that defines a minima or maxima. So it can either be an upper bound or a lower bound. Metrics define the values that you then use, right, to check whether a threshold exceeds or not at a time t. And then if it reaches for a certain period, usually, that's when you can take action. In this case, I'm showing what is an anomaly band, which is a upper and lower bound maxima, right? This is a scatter plot, but you notice that the values are drawn out, right? So this is a predictive model. So as you might have noticed, not all thresholds are the same, right? That is very different to what you would have defined as a threshold. And that's because the one we are aware of is static thresholds, right? Which is just a classic line through the noise, right? They are fixed, they're easy to estimate. They're also easy to diagnose. Like you can look at it straight up and know that, fine, this is not there, but they're also prone to noise, right? They can fail. They don't adjust well to the situations of your system, things like organic growth, etc, etc. And they're also single variates, right? You can either monitor CPU or memory, but in dynamic thresholds, you can use CPU and memory to define that, okay, fine, we need to scale the system, right? So auto-scaling models usually employ dynamic thresholds. And dynamic thresholds, in this case, they change with the metric observations. So they are boundary based, right? So that can be upper or lower, right? In the case of the anomaly bands I just showed you, they are always causal, so they rely on past and present data. And they are feedback loop driven. That's basically what the causal sense means, right? It's control systems, that kind of stuff. So they're multivariate, they adapt well, they're complex to align, right? You can't basically say this is where it's going to be, right? They need more tuning at the start because you also have to understand how your system is modeled, but they're less prone to false positives as a result of that. So definitions are done. So what's the process like for static thresholds? So to start off with a static threshold, you have a bunch of data points, right? So you need to filter out for outliers, right? To start off, right? Clean up the data, that kind of pre-processing, if you want to. It's not particularly a required process. But you can do so with things like IQRs and z-scores, right? Just to see just how well spread out your data is, right? Standard deviation also comes in here, but that's under z-scores. The second thing you do after that is that you define your aggregate statistic, which is like all these data points that are present, how do we make it one value? And you can do that with percentiles. You can also do that with a linear aggregate like a mean, right? Which is just an average. Or in this, there's geometric kind of means, but in this case, I mean a normal linear mean. So once you've done all of that, then you can reduce your mean error. I'm using something like the law of large numbers, which I'll explain in a bit. But this is like the entire process for static thresholds with numerical methods. So why do we need to filter for outliers? Is because static thresholds don't adapt. So that means that from the start, you need to be sure that is the normal band of your system that isn't really influenced by those outliers, right? So that's the skewness of your distribution. The kurtosis is reasonably fair, right? That's that bell curve distribution. Outlier filtering basically guarantees that you reduce the case of a false negative or a false positive, and you can keep it going from there. Now, interquartile ranges, as we've spoken about before for that filtering process, is very simple, right? And I highly recommend this, and then you can then move into more extreme methods, right? But this is very straightforward. The idea is that you take what the first and third quartile would be, right? You subtract them, which is the range part of the interquartile range. And then you basically define a minima and maxima using the first quartile minus 1.5 times that interquartile range, and then the third quartile plus 1.5 times that interquartile range. So it helps you like stabilize those numbers before you then go into predicting, where they should be. Now, the law of large numbers, as you'd have seen me mentioning, is basically a law that the average of a lot of results will converge towards the value that should be the result of that experiment. So if you had a lot of data points, say they are spread out, and say you took the P99 of the first 5 minutes, then of the next 5 minutes, and of the next 5 minutes in that like rolling window fashion, you might get 1 in the first one, 1 in the second one, 2 in the third one, 1 in the fourth one, 1 in the fifth one, right? That 2 is the outlier. But because of the fact that you have a lot of samples broken down, if you got the average of everything, it would converge below 2 and towards 1. And with the more samples you add, the larger the probability that it tends towards 1, which is your ideal mean. So that's the idea of the law of large numbers. It reduces the error case. So the way that you start it off is that you define a trend for what that system should behave like. In this case, this is a cron job that runs 3 times every minute. You can fail every time, it can pass once, it can pass twice, or it can pass all the time. You take those numbers and then you define what would be a logic table, right? With those sets of occurrences, can it fail all the time? Or can it pass all the time? And in that order, and then you basically throw it into what that trend formula would be. Because it's a static threshold, if it's predictive, you can do this. If it's non-predictive, then you can basically go about that P99 case I mentioned of just sampling by time, right? In this case, I can already know what the value would be at that time, and I can use that then to estimate what that trend would be like, and then just generate like my own data set for it. So yeah, so you run multiple iterations of that, right, using percentiles, or you can use an aggregate function, as we've already spoken about, mean, max, or a percentile. And then as you begin to then average that trend, you will get towards a value that meets that threshold. You can also guarantee the convergence using standard deviation, right? So in this case, this is like a sample of what that looks like from like when I do 1 and 10 iterations of each running. So 1 in the sense that there's only 1 cron job running, and 10 in the sense that there are 10 cron jobs running, those 3 iterative steps every minute, either health checks or whatever you use to define it. And then this is like what that random occurrence would look like if I were to take, say, the P90 or the P99.999. You notice the P90 has higher variation, right? So this would be nice if your system, say, had a lot of spikes, right? And it was very like jagged. And this P99.999 works in the sense that it's very predictive, it's always available, and you want to have very like strict SLOs. So the standard deviation will obviously capture this, right? Where you can see standard deviation for P90 is quite high. And as you then add more iterations, you'll notice it goes down. So this also then means that we're tending towards that convergence. So this is where the law of large numbers then plays a good part in running experiments like this, because you can be able to then define a way to then aggregate that value towards getting a threshold, and also then analyze whether like you are getting much closer towards the actual mean that you want rather than it's increasing. And in that case, you would see the standard deviation go up. Like in this case where you can see 100, 200, it decreases, 250, then increases again. So with more iterations, the P99.999 obviously has more variance, but the standard deviation is quite low. So you can obviously use that to judge based on your expectations. So yeah, but yeah, here's a graph of what that experiment looks like. You notice that the P90 threshold is close enough at 100 and 200 iterations, right? And it obviously then shows like what that range of values would be. So you can take all this data and then be able to define what that threshold value outcome should be like, what that heuristic estimates would fit into. And then this is basically how you apply the law of large numbers, right? And yeah, you can basically then define that static threshold. So that's basically what the law of large numbers is. It's a simple method for approximate static thresholds with predefined behavior. Even if it's not predefined, you can obviously then just use P99 to aggregate for that timeline. It allows you get clear methods on where that value should be at any given point in time, and then you can obviously then define it based on that your aggregate function, whether it's a sum, whether it's a percentile, whether it's an average. And then convergence across multiple data points implies the limits that captures where that threshold should be, and so you don't then have to guess, right? You've already proven that out, right, over a very large period of time with multiple iterations, experiments, and checks. So yeah, static thresholds are very easy, right? What about dynamic thresholds? How do we get there? Now, dynamic thresholds in platforms is usually called anomaly detection, but it's the same thing, right? So you want to basically capture whether the behavior of a system is outside what a predictive model would say it should be in, right? So again, dynamic, right? It's not fixed. So the idea is that you can build them on supervised models, right? So in this case, you get into machine learning or heuristical models. So things like logistical regression falls in here. You have a priori algorithms, things like clustering, unsupervised learning, and also curve fitting, which is just heuristical, right? So you just basically say, this is how I feel this trend should be, and then I can then find values that match it, and then I can then use that to then judge the fit against whatever sinusoidal behavior that system exhibits. So I'll talk about curve fitting because it's the one that I've done and I can show examples of, but all the other methods, I'll talk about them in a bit. So the basics to curve fitting is that you have like a series that exhibits like some sinusoidal or waveform like fashion, and then you're trying to then find what trend would fit on it, right? You can say it's a sine wave, a tan wave, a cos wave, like whichever way you want to express that waveform, even if it's exponential to the exact same way. So you start off like this. You basically define, say, curve fit. In this case, I've generated random data showing user sales in millions. It goes up and down across the hour. All of this is basically randomly distributed, but it still follows that sort of fashion. Then we then find a waveform that would fit it, right? And here you can see what the normal waveform would be, and here you can see what the curve would fit for it would be. Like I say, standard deviation is reasonably low, and then the fit is around 70%, right? So how do we get here? The idea is that remember that use case that we defined. So we obviously then have to estimate whether the fit is good or not. We can use the chi-squared good fit or standard deviation, which is used in chi-squared good fit. And then chi-squared good fit is better because it also takes into consideration the number of samples, as opposed to standard deviation where you're just checking the range of deviation from those of the samples from the mean. So you get there by taking A, B, and C. So A can be the amplitude, B can be, I guess, the phase multiplier, and then C is a constant, right? So you take all of those together, you then iterate across different values of A, B, and C to see like which one fits better, and then you then basically check what the error there would be. Or in this case, you can use the fit formula, right, to then judge like how well it actually fits the curve that you defined. For curve fitting, the variables are bounded, right? You can bound it based on, say, the amplitude of the curve, right? Like how high does it go? And then you can obviously then use that to then find, okay, fine. If A looks like it's tending towards a fit, then you can then change B and C to see whether it fits better or not. So that would be that regressive descent model for error correction. So yeah, it's very simple. It's very straightforward. There are also other methods for doing dynamic thresholds, right? Based on that machine learning phase of either you're doing anomaly bands, or in this case, you're just having one part trying to approximate what that threshold should be. You can use logistical regression methods, KNNs. You can use naive Bayes. Scalar vector machines also fit in here. And they also have, so these ones you would have classified data, they would be labeled properly, everything else. So this is more supervised. In case where you have like unsupervised methods, right? So you can use isolation forests. The case that I showed before of those anomaly bands with the upper and lower fits, right? You can obviously then use density-based scans. This example used PCA for filtering alignments and all those other bits. So this is also an example where you can do anomaly detection on random scatter plot data with unsupervised learning methods like density-based scans and PCAs. Yeah. The summary of all of this is that to basically use numerical methods, you can identify the business opportunities, like the case that I've mentioned with the dynamic thresholds for auto-scaling, or say in a non-technical sense where you're just trying to see whether user orders have increased so that you can scale operations. All these things and more, you can use them to basically predict what that value should be if it lies outside the fits, and then you can obviously then take action. Over time, organic growth and past data will influence this model, so they will just auto-fit over time. But at least now you can capture those trends without having to get paged every minute or two. Yeah, confirm whether you need dynamic or static thresholds, determine what the noise step should be. You can use scatter plots, you can use clustering methods, you can use IQRs, you can use z-scores. There's various ways to actually check whether your data set is fits for these methods or not. And then from there, just iterate until the error is minimized. A lot of these things are iterative methods, Monte Carlo in that sense. And whichever way you choose to define them, these are just methods. They don't particularly define the approach. But it's a good way to think about thresholds and statistics when you're modeling monitoring systems or just trying to improve the way that you iterate everywhere. Yeah. Thank you all. Again, you don't need to use all these guys sometimes. Eyeballing might be worth all of these, but if your systems behave in very weird ways, it might be worth a day or two with statistics to save you months of headache. Thank you all. Go forth and explore thresholds. Thank you.